My name is Michael Posman, and this is my Lab 3 video presentation. Introduction. So the purpose of this lab is to estimate the mass of a black hole using a star's orbital motion, and as well as simulate a spacecraft's orbit around a planet and its moon. Fundamental principles we used are Newton's second law, force equals mass times acceleration, Newton's law of gravitation, as you can see in the top right, F net perpendicular and F net parallel, the velocity and position update formulas, as you can see in the bottom right. The result of these labs were a massive black hole, is that number right there, and we got a relatively stable orbit for our spacecraft. So the reasoning, since we're in space, the only forces acting on the star orbiting the black hole are gravity of the acting on a star or the gravity. So F net equals the force of gravity. The star is in elliptical orbit, so the force of gravity is not constant. As it gets closer, the force of gravity is greater, and as it gets further, it's less. And we can use these equations to track the spacecraft movement in part two, and we can find the mass of the black hole using the force and movement of the star. So the mass of the black hole calculation. Here are the graphs that I got. Cyan represents the F net perpendicular. The magenta is the F net parallel, and the orange is just the force. The magenta arrow should be pointing forward, but I'll talk about why that's wrong later. The code for the mass of the black hole. So the initial conditions, the mass of the star is 2 to the 30. The first observation was that time step t equals 0, and delta t was 1 day, or that many seconds. And the gravitational constant is as normal. Ended up averaging up all of the values that we got throughout the entire calculation to get our final number using this code at the bottom right. This code at the left is you can see it, the change in velocity is the velocity final minus velocity initial, and F net is dp dt. The arrow scale was something I had to figure out, and also guessing and checking to make it to fit within our model. The orbit of the spacecraft model. So our initial conditions were ship speed, x equals there, y equals 2800. The system is the spacecraft, and the surrounding is the planet and the black hole. The reason that those specific initial velocities were used was guess and check. Couldn't make the spacecraft orbit in a perfect figure eight, but using those values, we probably got a pretty stable elliptical orbit. The code for the spacecraft orbit. So R in here is the position, and we use the Newton's equation, force over mass equals acceleration. We also use the gravity equation, as you can see here, because the F net on the ship is equal to the gravity of the F, the F on the planet, the force from the planet on the ship is the gravity equation between them, and you can use the values of R as we've defined up here to get the distances to put it into our gravity equation. And the velocity is how we use the F over m equals a. The acceleration times time equals our velocity, and you can use those down here. Sources of error. Source of error, we couldn't find the initial velocity to make a figure eight orbit. Tried guessing and checking, but couldn't get an exact value. The difference between real life and a model, like different things can go wrong in real life. There could be other nearby, other things in the way of the spaceship, and rounding errors always. But other than that, the model, it's a model, so could be pretty accurate. So what does it mean? The net force in the star is always directed towards the black hole, as is the only force acting on it, as I mentioned earlier. This force can be broken into two components, the parallel and perpendicular component, which affects the star's speed by either accelerating or decelerating it along its path, and the perpendicular component, which changes the star's direction and maintains its curved trajectory. The rate of change in momentum, or dp dt, follows the same breakdown, since momentum is directly related to velocity. Parallel component momentum changes corresponding to the variations in speed, while the perpendicular component dictates the curvature of the orbit. In a circular orbit, the only perpendicular component exists, keeping speed constant, whereas in an elliptical orbit, both components vary, leading to changes in velocity and trajectory. Understanding these relationships helps us explain how gravity governs orbital motion. So what if? To predict the motion of the entire system, the computational model would need to account for the gravitational interactions between all objects, the black hole, the star, the planet, moon, and spaceship. The dominant interaction would be the gravitational force between the black hole and the star, as the black hole has the largest mass and would influence the star's orbit the most. The planet's motion would be primarily affected by the star's gravity, while the moon's motion would be dictated by both the planet and, to a lesser extent, the star. The spaceship's trajectory would be the most complex, as it would be influenced by the gravitation of the moon, the planet, and possibly even the star, while all interactions could contribute to the system's dynamics. The black hole, star, planet, moon interactions would be the most significant, with smaller bodies experiencing more localized gravitational effects. Thank you.